Hello everyone, welcome to PNU 202, PGE's Customer and Operational Improvement Journey with AWS. I am Joe Beer, the Worldwide Technical Leader for AWS's Power and Utilities vertical. In this session today, you're going to hear from Portland General Electric, better known as PGE, about their digital cloud journey and the successes they're having using AWS Cloud Services in the OT transformation and customer engagement area. But first, I'm going to spend a few minutes setting the context for the talk and talking about the disruptors impacting the utility industry today. And then you're going to hear how Uma and Sung at PGE are addressing these disruptions against the traditional utility value chain. So speaking of that value chain, I'm going to show you right now the traditional one, which is very linear. It's the one that's been around for about 100 years, and Thomas Edison, George Westinghouse would recognize this. It goes from generations straight through to the consumers of energy. What's been happening, though, is these disruptors are entering the picture. Decarbonization, decentralization, and digitization, all on top of the existing disruptor of deregulation, which has been around for about 10 years. Decarbonization refers to the need to take carbon out of the grid so we can meet society's requirement for sustainability. Decentralization refers to the oftentimes smaller and renewable energy resources being moved closer to the point of consumption. And these are usually wind and solar resources. Collectively, these are known as DERs, or distributed energy resources. And then digitization is all about handling the flood of data coming from these new energy resources to let customers frictionlessly manage their energy in an engaging way. It's also about weaving everything together with IoT, AI/ML, smart home technology, and data and analytics so that there's a seamless experience to manage that energy, whether you're a homeowner or a business owner. The result of these disruptions is the change value chain, which you see here. You've got distributed energy resources on the lower left, and then you have your more sophisticated energy consumers on the right. You also have arrows going two ways, indicating the selling of electricity or energy back into the grid by non-utility entities, such as prosumers and commercial and industrial customers. You notice that EVs also play a large role, and that's only going to increase as states and municipalities put more and more laws on the books to outright ban petroleum vehicles. So how are utilities going to address this change in the value chain? Well, they need flexibility. They need flexibility across the value chain, and that flexibility is enabled with digital transformation. They need flexible generation to be able to handle the growing quantity of the intermittent renewable energy resources being put on the grid, both the big grid scale systems that they're putting in themselves, as well as the smaller scale that business and prosumers are putting on the grid. They need flexible delivery so they can optimize the trading of energy and aggregate DERs into a single virtual power plant, and then dispatch these up and down, or dispatch means turn on and off, basically. Dispatch these to the grid to meet the changing needs of customer demand as well as changing weather patterns. And then they need flexible demand to be able to influence or actually outright control the demand curve to ensure stable power for all at the most cost-effective rate. And this is going to be especially important in parts of the grid that are older, where perhaps they don't have extra capacity in the distribution network, and EVs and DERs approach that 10% mark, because it's predicted that once they hit that, if the grid's not up to snuff, you're going to have brownouts and blackouts. And digital transformation also provides utilities with the extra capacity to focus deeper on their core objectives of providing reliable, safe, and secure power, greater agility and quicker time to market with new products and services, increasing customer satisfaction, as well as optimizing the revenues and costs. Our belief, and the belief of many leading analysts, is that by adopting the best practices of digital transformation and digital enterprises and leveraging the power of cloud like AWS are the best mechanisms by which utilities can meet their digital transformation challenges. So we see utilities transforming themselves in 5 broad areas with business outcome-driven solutions. These are IT transformation, OT transformation, work and asset optimization, energy supply transition, and customer engagement, all supported by a common layer of data and insights. Portland General Electric has focused on 3 of these areas: the OT transformation space, customer engagement, and data insights. You're going to hear from Uma and Sung in a minute about how they address these challenges. But before I hand the reins over, I'll just give you a glimpse here of some of our customers around the globe, customers and partners that are on their digital transformation journey with us. You'll notice many utilities here, as well as end OEMs that manufacture equipment for the utility industry, like the GEs and Siemens of the world, Schneider. We have the software providers in the utility space, such as AutoGrid and Imprest. We have the big systems integrators as well, and the small ones, Accenture, Deloitte, Tech Mahindra, etc. So with that, I will now turn things over to Portland General Electric, Sungyang Soon, Senior Data Scientist, and Uma Venkatachalam, Principal Information Architect. Very proud to have them here speaking and presenting to you. PGE, take it away.
Thank you, Joe. Hello, everyone. My colleague Sung and I are very excited to present about Portland General Electric's digital transformation journey and how we used AWS to accelerate it. We will be sharing few learnings along the way. Portland General Electric has been serving power to Oregon for more than 130 years. We are a vertically integrated utility handling generation, transmission, and distribution. We are an investor-owned electric utility serving most of Oregon. Here are a couple of highlights from our clean energy journey. Our residential and business customers helped us develop the #1 renewable power program in the nation, with a quarter of our customers voluntarily paying a little extra towards clean energy. We are developing the Wheat Ridge Renewable Energy Facility, the first in the nation that combines solar and wind generation together with battery storage in one location. In line with our clean energy future, our 3 long-term imperatives are to decarbonize, electrify, and perform. 2 of our important goals for 2020 are to reduce customer friction and to increase operational efficiency. Our digital transformation is the core foundation to help us achieve our imperatives and goals. Translating that to IT, here are some measures of success. On the reliability side, we want to increase the uptime and availability for our applications and reduce customer impacting events. On the cost side, we want to be the top quartile IT operator by optimizing cost and value. One of the important success measures is performance and scalability. We want to be able to serve our customers during peak demand times, like during an outage. On improving cycle time, we want to provide value to our customers at a faster pace and higher velocity. Sung and I are going to present few different use cases to highlight our AWS journey in the last year. The first use case is the API microservices platform for our digital channels that help reduce customer friction. Next, I will be talking about the data lake and the principles behind the data lake, and also a solution on the data lake, which is the metadata analytics for energy loss detection. Following that, Sung will be presenting few of advanced analytics use cases. The first one is the API microservices architecture. We want to empower our customers to enable their own customer energy journeys. As part of it, we want to provide an omni-channel experience to our customers, where the customers can log in from any of the channels, the mobile, the web, or IVA, to perform a function like making a payment, viewing or reporting an outage, or to manage their products and programs. AWS helps us build the API microservices to serve data to our digital channels. This is the high-level architecture behind our API microservices platform. Here, if you see the steps 1 through 4, show how we replicate data from on-premise and pre-stage it in the DynamoDB. We use AWS Database Migration Service to replicate data from our on-premise systems like the customer information system or the outage management system to land it in a Postgres RDS. Then we use Lambda to apply business logic and transformation to pre-stage data in the DynamoDB. When a customer logs in via a mobile app or a web, steps A to C show how the interaction happens. The data is served to the customer from the pre-stage DynamoDB database through the API gateway and Lambda. Steps D, E, and F show how data is posted back to our legacy systems through the queues and Lambda. With this architecture, we were able to provide a layer of abstraction from the on-premise systems to serve our customers better. Let me share with you a couple of learnings as part of our architecture. When we started out, we used the AWS database migration service, but we found out some incompatibilities where the DMS was not able to work with pluggable and encrypted Oracle databases. Eventually, this issue was fixed. When we started out, we also debated whether we want to go with DynamoDB as our target database or to go with RDS. Since we were more familiar with the relational databases, we went ahead with using RDS for our initial implementation, though we knew that there could be some downtimes as part of patching. In the last year, we have learned much more about our data access patterns, and we have migrated to DynamoDB. Here are some high-level results from the new API microservices platform. In the recent major outage event, our APIs were able to serve 5 times the number of customer visits in 1/4 the response time compared to the on-premise APIs. On the reliability side, we were able to reduce our planned downtimes by more than 1/10. All this has helped increase customer satisfaction. After we launched our new website, we were able to see a 10-point increase in Net Promoter Score and satisfaction with the digital experience based on customer surveys. Next is the data lake. There is growing data needs for electric utility. One of our goals is to harness data and analytics to drive business decisions and to be able to come up with innovative products at a faster pace. Our data lake is purpose-built and use-case driven for the data solutions that we are building. To give an example, for a data solution to recommend energy-efficient products to customers, we need to build a digital thread of data from the legacy customer information system and from the behind-the-meter information, like if the customer owns a solar panel or electric vehicle, and combine that with the meter consumption patterns from the smart meters, and maybe some external data like the customer demographics. Our data lake has evolved based on the data solutions that we are building. This is the high-level architecture for the data lake. We ingest data from our on-premise systems using the AWS database migration service. We also ingest data from third-party systems using Lambda and Matillion to stage it in S3. Snowflake is our data lake data warehouse platform. We use Matillion and Glue to pre-process data into the data lake. We are in the process of setting up an internal data marketplace where data from different sources are consolidated into one place like Asset 360 or a Customer 360 so that users can use the data from the single place instead of going after siloed systems. We use Amazon QuickSight and Tableau for visualization. Our data scientists use Amazon SageMaker for developing their ML algorithms using data from the data lake. Underlying all that is the foundation of governance and security. When we started out, we used Redshift, but soon we pivoted to Snowflake due to the flexibility of separating compute and storage available at that time with Snowflake. On a few occasions, we ran into issues replicating huge volumes of data from on-premise to AWS with VPN connectivity. Direct Connect is recommended for large data replication. Here is a summary of some of our results from the data lake. As part of the cloud-first strategy, we are in the process of sunsetting some of our on-premise data marts and data warehouses and move them to the cloud. We are looking at a savings of more than $3 million in the next couple of years with this simplification effort. On the scalability side, Data Lake gives us the ability to isolate and increase compute independent of storage. To give an example, recently we had to share the billion rows of AMI meter data with a distributed energy resources partner. We were able to spin up a new compute and share the data within 1 hour, while the same thing would have taken a few days to complete if we tried to extract the data from on-premise. One other example for customer satisfaction is the energy usage sharing platform that we have set up with the Environmental Protection Agency for some of our businesses and cities. With this, our customers are able to share their energy usage with EPA and track their greenhouse gas emissions towards their decarbonization goals. Prior to this energy sharing platform, each customer was spending more than 160 hours entering this data manually into the EPA website. With the new solution, everything is automated and seamless. The next is a metadata analytics solution that we have built on the data lake for energy loss detection. Energy loss detection is an issue to any utility in regards to revenue protection and also for safety reasons. We had a prior vendor solution whose accuracy rate was pretty low, causing unnecessary field visits. We built the in-house solution on the data lake, and we were able to increase the accuracy by more than 50%. We also saved more than $600,000 in vendor costs and avoided field visits. We were able to recover more than $1 million in unused billing with this new solution. The metadata analytics is a core foundation to many other algorithms and data solutions in the future. Over to you, Sung.
Thank you, Uma. Hello, everyone. I'm Sung Jun-yoon, a senior data scientist at PGE. Today, I'm going to introduce 3 machine learning solutions our data scientist team has developed. First, I will talk about how we built a machine learning solution to provide accurate estimation of restoration time upon outages. If you think about an outage you recently experienced, the most wanted information during the outage is when your power will be back on so that you can plan ahead. PGE provides outage information through multiple channels: website, mobile app, and IVR. The image on the left is a snapshot of our mobile app with outage information. However, outage information is only available when customer logs into their app or website, or they call in to report outages. Upon outage, we want to notify our customers proactively about the outage and provide the most accurate restoration time estimation as soon as customer meters detects outage. Once our outage management system, which is a legacy system for many utilities, provides initial outage restoration estimation. However, there are many times they are inaccurate, and often they get updated multiple times as crews update outage information. We want to provide an accurate outage restoration estimation when customers meter detect outage. To meet this goal, we built a machine learning model from historic outage events, weather condition right before the outage, and the location and size of the outage. As you can see from the chart, we saw more than doubled accuracy improvement with our new model compared to the current system. We used SageMaker to train and host our model behind an endpoint with the auto-scale feature. Utilizing Amazon's simple notification service, we developed infrastructure to message customers the model predicted restoration time. And this solution is expected not only to improve customer experience during outage, but also to reduce about 700,000 notifications per year by providing accurate outage restoration time at the onset of the outage. It is also expected to save field crews' effort to update outage information multiple times while they work hard to restore powers during outage. In the next slide, I want to introduce our solar generation prediction model. We saw strong growth of solar panel adaptation among our customers in the recent years. Last year, total solar capacity among our customers has grown by 20%, and the rate has been accelerated. When customers install solar panels, most of the times they want to send back leftover energy to our grid and get credit for it. However, PGE is regulated to measure only net energy flow from customers. Thus, we do not have visibility to the generation from customer side. These invisible generation from customer side can cause grid overloaded with excess customer energy generation and result in safety power cutoff from our substations or bad power quality from customer side. To prevent all these adversary effects from solar generation, our engineers have spent considerable amount of time and effort to make sure our grid has enough capacity before customer installs new solar panels. And this long and manual process is expected to get worse as we expect customer solar generation will accelerate in the near future. To give better experience for our solar customers, our team has developed a solar generation prediction model to predict their generation for each of the solar customers in our service territory. We took time series net consumption data from AMI meters, and we also took solar panel capacity information and weather information such as cloud coverage, snow precipitation, and temperature. We performed time series feature extraction and trained a neural net model to predict solar generation. At the end, we were able to achieve 3.1% of mean absolute percentage error, which means our model generated solar generation is different from actual generation by 3.1% on average. The graph here shows time series of solar generation, prediction versus actual from an example residential solar customer. As you can see, the predicted generation matches pretty well with the actual generation. This model is implemented using SageMaker Batch Transform API and Lambda for scheduled inference and training. As an obvious benefit of this model is to reduce more than 50% of process time in reviewing grid capacity for new solar installation. And the result from this model is expected to be used for as key information for distributed resource planning, DRP, to properly plan out our grid assets to meet our customers' demand to use cheaper green energy. Lastly, I'd like to talk about PGE's effort on condition-based asset maintenance, especially for wood poles. Many electric utilities rely on age-based asset replacement program. However, studies found that wood poles' life expectancy can vary a lot by surrounding conditions, such as localized weather condition or ecosystem around the poles. To identify poles at risk based on actual physical condition, PGE has been running a program called Full Pole Inspection. This inspection is to identify poles at risk with physical damage, and we identify and fix or replace those poles before they fail. So far, the inspection program has selected target poles based on subject matter expertise. Because of human judgment, sometimes those pole selection has been inconsistent year over year, and the chance that the inspection program actually finds the truly bad poles were quite low. If this inspection program cannot find bad poles at the right time, it can potentially cause a significant impact to our customers. To improve the success rate of the inspection program and create consistency in pole selection, we created a model to predict pole failure probabilities. There are three major wood pole damage mechanisms. split top, woodpecker damage, and decay. Utilizing pole information such as age, wood types, attached assets, and weather information and ecosystem information surrounding the poles, we built a successful model to predict pole failure probabilities for the 3 damage types. In combination, we were able to achieve 0.82 F1 score, which means the model predicts good and bad poles with 82% accuracy on average. The predicted result is plotted on the map on the left side. Split top occurs more frequently on aged poles, which concentrated in urban area in our service territory. As you can see, the same trend in the red color is dominating in the Portland metro area. Also, woodpecker damage is expected to be concentrated in rural area. We see that yellow color is spreading out in the rural area in this result as well. As a result, the model is expected to improve bad pole detection efficiency by 65%. And with this improvement, we expect to see reduction of unplanned outage due to wood pole damages. In the next slide, I want to talk about how AWS technology was used to create a framework to develop and deploy machine learning models in our team. First of all, AWS Cloud and Data Lake with proper governance and security has reduced siloed database in our company. This significantly reduced effort from our data scientists in finding and getting access to the database and cleaning data set as the data quality in the data lake has improved significantly. SageMaker has been very useful in both prototyping and production. Serverless nature of the SageMaker enabled us to do fast turnaround in model tuning and training and showing the result. Once a model is trained, we measure the performance of the model. If the performance exceeds the success criteria, we move the model into production. Our models are served as SageMaker endpoints. We found auto-scale and load balancing feature in SageMaker especially helped us to move faster by eliminating the need to build and maintain container orchestration infrastructure. Amazon API Gateway with Lambda served to interface client's application. From data to the APIs, getting requests from client, everything was built natively in AWS. It made our machine learning workflow much faster than our on-prem solution. Personally, I believe that a success of a data science team in a company largely depend on a simple, reliable machine learning development and deployment framework. I and my data scientist at PGE successfully utilized SageMaker and AWS cloud infrastructure to develop and deploy machine learning solutions. Thank you, and to Uma to discuss our learnings.
Thank you, Sung. Here is a summary of some of our learnings. We believe in just-in-time training. When we did our initial implementation on AWS for our APIs and microservices, our team was able to ramp up on the AWS technologies and deliver the first set of APIs within 3 months. Since then, our developers have taken few different AWS certifications and also have participated in hackathons as part of their learning journey. We also recommending developers to break down silos between an API engineer or a data pipeline engineer versus an ML ops engineer. It goes without saying that continuous integration delivery, DevOps, and deployment test automation are a must for increasing velocity. We use both Terraform and CloudFormation as part of our infrastructure as a code. We also highly recommend using the AWS well-architected review with the 5 pillars of operational efficiency, reliability, security, performance, and cost optimization as part of your solutions. It's ideal to start using the well-architected framework during the design phase and iterate through it as you productionize your solution. Our preference is to use the serverless components as much as possible. And AWS has also helped us experiment, learn, and course correct on our journey. Thank you for listening to our AWS journey. Please take the feedback. We really appreciate your feedback. Thank you.